This is part 2 of the Chapter 4 notes. The example at the top of page 6 says, according to the National Vital Statistics Report, 20.1% of all pregnancies result in a weight gain in excess of 40 pounds for a single birth. In addition, 49.5% of all pregnancies result in the birth of a baby girl. Assuming gender and weight gain are independent, what is the probability that a randomly selected pregnancy results in a girl and weight gain in excess of 40 pounds? So since this says that these are independent from the last video, we have a formula up above on the bottom of page 5. This is the probability of A and B is equal to the probability of A times the probability of B, only if they are independent. And for this problem, it does tell us that they're independent. So the probability of having a girl and a weight gain of 40 plus pounds is equal to the probability of having a girl times the probability of a weight gain of 40 pounds or more. And so looking at our problem, we know that the probability of having a girl is given as 49.5%. So 49.5%, we need to change to a decimal, and we need to move our decimal point twice to the left. And so for probability of having a girl, it's 0.495. Likewise, the probability of having a weight gain of 40 pounds or more is also given to us, and this is 20.1%. So again, moving your decimal point twice to the left, you get 0.201. And for this, we just are going to put these in on our calculator and multiply them. Rounding our answer 4 decimal places, we get 0.0995. And again, the reason why we were able to use this formula is because they were independent. Right underneath the example, it says sampling with replacements and sampling without replacements. So sampling with replacements is selections are independent of one another. In sampling without replacements, they are dependent of each other. So sampling with replacements is like if you were to grab something like a sock out of a drawer and then put it back in the drawer, whereas sampling without replacements would be taking that sock and putting it on your foot. So that changes what is in that drawer for the second pick. When sampling without replacements and the sample size is no more than 5% of the size of the population, treat the selections as being independent, even though they're actually dependent. So the next example we have says assume that 3 adults are randomly selected without replacement from the 258,418,544 adults in the United States. Also assume that 10% of adults in the United States use drugs. Find the probability that the 3 selected adults use drugs. So for this problem, we are selecting somebody. We are not putting them back into that population, but then we select another person, don't put them back, and then select a third. That way we don't select the same person twice. Since we have such a large population, that 258 million, and we're only sampling 3 people, this is less than 5% of that population size. So we're able to treat this as independent. So I'm going to say assume independence. And again, that is due to the fact up here that says that the sample size is no more than 5% of the population. And 3 people is very small percentage of the population size, which was at 258 million. Okay, so then we're looking for the probability that all 3 use drugs. So to say all 3 use drugs. And so using the formula that we used in the previous example and also at the bottom of page 5, this is going to be the probability the first uses drugs times the probability the second uses drugs times the probability that the third uses drugs. And so from this, we know that 10% of adults use drugs. And again, we need to change our percent to a decimal, moving your decimal point twice to the left, we get 0.10. And so the probability that the first person uses drugs is 0.10. probably the second person uses drugs is 0.10, and probably the third person uses drugs is 0.10. Multiplying this all out on our calculator, we get 0.001. Right below this is section 4.3, which is using complements to compute at least one probabilities. Computing at least probabilities typically uses complement rules. The phrase at least means greater than or equal to. So at least one means one or more. So at least one is going to equal 1 minus the probability of no occurrences. And this is due to the fact that at least one means one or more. So the only event that we're not looking at is going to be no occurrences. And so remember, the total adding up that sum of all those probabilities is equal to 1, and then minus that probability of no occurrence. The example right below says among Americans who consider themselves avid bakers, 59% said their favorite thing to bake is cookies. Suppose that 4 avid bakers are randomly selected. So because we're dealing with people, they are independent of one another. And also, we're selecting 4 different people. So part A says, what is the probability that all 4 say their favorite item to bake is cookies? So the probability all say cookies is going to be the probability the first likes cookies times the probability the second like cookies, the third favorite thing is cookies, and the fourth favorite thing is cookies. And so from this, we know the probability that their favorite thing to bake is cookies. The percent was 59%, which again, moving your decimal point twice to the left, is going to be 0.59 times 0.59 times 0.59, and then times 0.59. You can also write this with an exponent and say 0.59 to the fourth. When you do this and you multiply it out using your calculator, you get 0.1212. Part B says, what is the probability that none will say their favorite thing is cookies? So if your probability of favorite item to bake is cookies, then the probability of not having the favorite thing be cookies would be 1 minus the 0.59, which is 0.41. So the probability not cookies is going to be the probability, and we'll say all 4 are not liking to bake cookies, is going to be the probability the first is not cookies, the second is not cookies, the third is not cookies, and the fourth is also not cookies. And so this is 0.41, and you can multiply it 4 times, or as we stated before, to the 4th power. To do 0.41 to the 4th power, we're going to do 0.41, and then you'll have a little caret. It's right above the division symbol, and this is raising it up to the 4th power, and then selecting enter, and we get our decimal answer. Using your calculator to do 0.41 times itself 4 times, or using the exponent button and raising this up to the 4th power, we get an answer of 0.0283. Part C says, what is the probability that at least one? So now we have that at least one that we talked up above about, and at least one will say their favorite item to bake is cookies. So probability at least one is going to like to bake cookies. So this means either 1 does, or 2 do, or 3, or 4. So the only case that we're not looking at is that nobody likes to bake cookies. And so we're going to use that complement, 1 minus the probability that all 4 not baking cookies. And we calculated this above. And so we're going to have 1 minus 0.0283. And so subtracting this on our calculator, we get 0.9717. At the top of the next page is section 4.4, which is on counting. And this says there's a multiplication rule for counting. And it says if a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, and R selections for the third choice, and so on, then the task of selecting these all would be P times Q times R times and however many more you have different ways. And so from here, we have an example that says how many different current California license plates can be created using the standard setup, no special characters, no spacing. So this is just a basic license plate. It says the standard setup is going to be a number followed by 3 letters followed by 3 numbers. So for this, we're going to have to ask first thing, does order matter? And kind of keep this in mind. And for a license plate, yes, the order does matter. And so I'm going to put some dashes here. It says the first thing is going to be a number followed by 3 letters and then followed by 3 numbers. So how many total numbers are there that could go in that first spot? So 0 through 9 is going to give us 10 different possible values that could go there. And then how many letters do we have in the alphabet? In our English alphabet, we have 26. And letters can repeat. So for this, just because the first letter was an A doesn't mean the second one cannot be an A. So there's 26 also possible values that could go here. Likewise with the third spot, since those are all letters. The last thing is numbers, and they could repeat also. Just because your first digit was a 7 doesn't mean you can't have a 7 again. So 10 in each of these places. And then as the formula states up above, we're going to multiply in between all of these. And so on your calculator, you need to do 10 times 26 times 26 times 26 times 10 times 10 times 10. When you plug this in on your calculator, you get 175,760,000. And these are California license plates. So making sure that you have a label, like this one is California license plates, when you do these types of problems. So the next example that we have says a social security number is used to identify each resident in the United States uniquely. The number is of the form, and in those X's there, it says where each X is a digit from 0 through 9. So in other words, a digit 0 through 9, we talked about this, there's 10 different possible numbers that could be. It says how many social security numbers can be formed. So again, the setup is 1, 2, 3, then a little dash, and then 1, 2, and then dash, and then 1, 2, 3, 4. And in each of these spots, we can put a 10. And then again, from here, we're going to be multiplying all of these digits together. And when you do this, and you multiply it out, you're going to get 1 billion. And this is the total number of social security numbers. The next part, B, says what is the probability of correctly guessing the social security number of the U.S. president? So the probability of correctly guessing this, so the social security number is going to be, the denominator is going to be that 1 billion that we had up above. Those are all the different possible social security numbers that we do have. And then since we only have one president right now, that means that there is only one social security number for that president. And so this is going to be 1 divided by, and then that 1 billion. When you do this, you get 1e to the -9th, or remember this is 1 times 10 to the -9th, or moving your decimal place 9 spaces to the left, we get if you were asked to round 4 decimal places, this would just round to 0.0000 or just plain old 0. The next thing that we have is called a factorial. This is denoted with an exclamation mark. This says if n is greater than or equal to 0 is an integer, then n factorial is n times n minus 1 times n minus 2 times 3, 2, 1, all the way down to 1. Note 0 factorial is 1 and 1 factorial is also 1. So on the example right below, it says 15 students in a class are asked to line up for a class picture. How many different ways can they line up? So if you had 15 different spaces here, and I'm not going to write them all out just because that's a lot of spaces, but how many students could be first in that picture? There's 15 different students that could be first. Now let's say Tommy is already standing up there and he's the first student. So now he's already standing up there and the class size is now down to 14 since he's already standing up there. So 14 students can go into the next spot. Let's say Jane stands in the next spot. So it goes Tommy, then Jane, and then there's 13 other students that are sitting there that could go to the next. And this process goes on and on and on until we get to the last final few students. So multiplying all these numbers, you would have to take some time to plug that in, but notice that this is the same thing as 15 factorial. And so on your calculator right now, we'll talk about how to use the graphing calculator to make this go a little bit faster. But for right now, if you were to plug in 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, we're going to get 1.308 E12, which again, remember this is 1.308 times 10 to the 12th. And since this is a positive exponent, we need to move our exponent 12 times to the right. And so we would have a really large number. I'm going to leave this one in scientific notation. At the bottom, we have permutations and combinations. Permutation is the number of arrangements of R objects chosen from N objects in which 1. The objects are distinct, repetition of objects is not allowed, and the third one, which is really important here, is order is important. AB is different from BA. And so we have a formula here. The formulas we're not going to be using since we will be using our graphing calculator instead to compute these. The next definition we have is combinations. This is the number of arrangements of R objects chosen from N objects in which the N objects are distinct, repetition of objects is not allowed, and for this one, order is not important. So this means AB is the same as BA. And so this is given by, and we have a formula also here that we will not be using. Instead, we will be using the graphing calculator, and the steps are on the next page. So on the next page, this says permutations and combinations with the TI-8384 calculator. Also notice that we have factorial also listed on there. And so from this, you are going to go to your math button on your graphing calculator and look for P. It either says PROB on your calculator or PRB. There's two different ways that the graphing calculators have that written. And then you'll notice that there's one that says NPR and then another one that says NCR and then another one that says exclamation mark, which is our factorial. So remember, permutations is where order matters. And the second one, our combination, is order does not matter. So a few things with this is that you're going to be reading these word problems and asking yourself, does order matter or does order not matter? So for example, races, order matters, but selecting maybe a group of students to come up to the board or to have volunteers, it doesn't matter if you're picked first or if you're picked last, you're still one of those volunteers that's coming up to the board. So for the example right below, this says find the value with using your calculator. And so we need to go to our math button, to probability, and then select exactly what this is. So on your calculator, see if you can try these. On the graphing calculator, to go to probability, we select our math button, go right to PRB or PROB, and you'll notice that you have your NPR, NCR, and factorial. The first one that we have is 7 factorial, so I'm going to go 7 first, and then factorial, and then enter. For part B, we have 0 factorial, for part C, we have 11 factorial, so math, PROB, factorial, enter. And so writing down our answers for A, B, and C. The next three focus on permutations. So for D, this says 9 is our first number. And then we go to math, PROB, NPR. So since this is a probability, and then the second digit that we have is 0, select enter. For part E, we have 9, go to math, PROB, permutations, and the second digit that we have is a 4, select enter. And then for F, we have 9, then go to math, PRB, NPR, second digit's a 9, select enter. For G, the last row, we have combinations. So similar idea, we type the first digit, then go to math, PRB or PROB, combinations, select the NCR, and then 0, enter. The next one that we have is 9, math, PRB, NCR, type the 4, select enter. The last one that we have is 9, math, PRB, NCR, and then 9, select enter, and we get 1. So from the graphing calculator, we get the results below. Permutations, when some items are identical to others. The number of permutations of n objects in which n1 are of one kind, n2 of another, and n3 of a third, and then nk of a kth kind is going to be n factorial divided by n1 factorial, n2 factorial, n all the way through. So the example right below says, when designing a survey, pollsters sometimes repeat the question to see if subjects are thoroughly and thoughtfully providing answers or just trying to finish quickly. For a particular survey with 10 questions, 2 of the questions are identical to each other and 3 other questions are also identical to each other. For this survey, how many different arrangements are possible? So we have a total of 10 questions, so that is our numerator. And we have 10 factorial over. And then the items that are repeating, so there's 2 questions that are identical, so we're going to have 2 factorial times, and then we also have 3 factorial because 3 of the questions are also identical. On the graphing calculator in the numerator, we have 10 factorial, so go to math, PRB, and then factorial. I'm going to go ahead and get my numerator value, and then the denominator is going to be 2, and then again do math, PRB, factorial, times 3 math, PRB, factorial, and I get my denominator. So now I'm going to divide my numerator. I can highlight that number and select enter, or you could just retype it, and then I'm going to divide it by, and you can highlight 12. I'm just going to type 12 though. When doing this, I get my answer. We're going to end up with 302400, and these are different arrangements for a survey. The example right below says, in the U.S. Senate, there are 21 members on the Committee of Banking, Housing, and Urban Affairs. 9 of these 21 members are selected to be on a subcommittee of economic policy. How many different committees structures are possible for the subcommittee? So the first thing you need to ask yourself is, does order matter? And for a committee, it doesn't matter if you're selected first or if you're selected last, you're still part of that committee. So order, not important. And since order is not important, we know that we are using combinations. So I'm going to go ahead and put a giant C there for combinations. And then I'm going to put my little sub numbers so that I can use my formula. So the sub numbers are going to be N and R. So N, the first one, is the sample size that you have. So how many people are we selecting from? And that's 21. And then the second number is how many are we choosing for that subcommittee? And it tells us that there are 9 people that we are selecting. On the graphing calculator, we need to type in the first number, which is 21. Then go to Math, PRB. This is a combinations. And then type 9. Select Enter, and we get our result. From the graphing calculator, we get 293,930 subcommittees that are possible. The example right below says, in how many ways can gold and silver medals, which is first and second place, be awarded in a 10-horse race? So for this one, since we are dealing with a race, order is important. And because order is important, we know we are dealing with permutations. So I'm going to put a P there. Again, that first number is how many people we can select from, or how many horses in this case, which is 10. And then the second digit is going to be what we are looking for. So for this one, it's going to be the first and second place horses. So that's 2 horses. On the graphing calculator, the first digit that we have is 10. Then we need to go to Math, PRB or PROB, and select permutations, the one with a P, and then the second digit that we have is a 2. Select Enter, and then we get our answer. So from our graphing calculator, we get 90, and this is going to be ways for 2 horses to finish. The example at the top of the next page, suppose that there are 55 Democrats and 45 Republicans in the U.S. Senate. A committee of 7 senators is to be formed by selecting members of the Senate randomly. So again, we're dealing with committees, so order is not important. Doesn't matter if you're first selected or last, you're still part of that. So part A says, what is the probability that the committee consists of all Democrats? So the first thing that we're going to talk about here is that we're talking about probability, and we need to have a sample size. Since order is not important, I'm going to put a C. That sample size I'm going to use to represent, I'm going to put an N. How many total people can we select from? And so for this problem, there was 55 Democrats and 45 Republicans. So total, this is going to equal 100. So we have 100 different people we can select from, and for this committee, it's going to be just 7 that we are looking for. So 100, choose 7. Now it asks for what is the probability that we have 7 Democrats and 0 Republicans. So for this, it's wanting a committee composed of all Democrats. So since we're asking about probability, I'm going to go ahead and draw a line here and talk about our denominator and our numerator. And so our denominator is going to be that sample that we just came up with, which is going to be 100. Choose 7. For the numerator, I'm going to look at each of these things individually. So we have 2 groups. So we have Democrats and we have Republicans. And so up in the numerator, I'm going to write Democrats and Republicans. And since we're still dealing with these committees, we still have a C, since order is not important to us. And so the Democratic people we're going to look at first. Total, there was a total of 55 Democrats we can select from. And we are selecting 7 since it says all Democrats. Whereas the Republicans, there are 45. And we don't want any Republicans to be selected for Part A. The symbol and, or the word and, is going to mean multiplication. So we need to substitute all of this in on our calculator. On the graphing calculator, I'm going to type in the numerator first, which the first digit is 55. I'm going to go to math, probability, NCR, and the second digit that we have is 7. Right now it's currently in the little bottom part of this. I want to make sure that it's not, so I'm going to go next to, so I use the right arrow. I'm going to select times. And then the next digit that we have is 45. And then math, PRB, NCR, and we're selecting 0 here. Doing this, I get my result. And then I'm going to divide this, I'm going to hit the division symbol, by my denominator, which is 100, math, NPR, again select combinations, second digit is a 7, and select enter. Make sure to round this correct to 4 decimal places. From the graphing calculator, rounding 4 decimal places, we get 0.0127. Part B says, what is the probability that the committee is going to consist of 3 Democrats and 4 Republicans this time? So this time we're looking for 3 Democrats and 4 Republicans. It's asking about probability again, so we're going to split and have a denominator and a numerator. That denominator is still going to be the same. And then the top, the same idea, I'm going to do Democrats and Republicans and put C's above both. And so total Democrats that we have to select from is 55. That has not changed. But for this problem, we only want to select 3. Whereas Republicans, we have a total of 45. And for this one, we only want to select 4. And the word and means multiply. So we need to substitute this all into our graphing calculator. On the graphing calculator, we're going to type in the numerator first. The first digit we have is 55. Then we go to math, probability, and then make sure to select NCR for combinations. The second digit that we have here is a 3. Use your right arrow so that your cursor, the flashing part, is next to the C and not the 3. So times. And then our next digit that we have is 45. Again, math, go right to PRB, select NCR for combinations. Second digit we have here is a 4. Select enter and we get our numerator. I am then going to divide that A and S is pulling that answer from right up above. And I'm going to divide 100, go to math, probability, NCR again for combinations, and then 7. Select enter, and we get our probability. From the graphing calculator, in rounding 4 decimal places, we get 0.2442. The next example, right below, says, suppose that you have just received a shipment of 100 TVs. Although you don't know it, 6 are defective. To determine whether you will accept the shipment, you randomly select 5 TVs to test them. If all 5 TVs work, then you accept the shipment. Otherwise, the shipment is rejected. What is the probability of accepting the shipment? So again, just like as above, we had Democrats and Republicans. This one we have TVs that are working and TVs that are not working or that are defective. And so for this, order does not matter. And the reason why order is not important is because when you select them, you are testing them. So you would select 5 TVs, you're going to test them. It doesn't matter if it's the first one to be tested or the 6th one to be, or the 5th one to be tested. It's all going to have the same result. So how many total TVs are defective is 6. That means that if you had 100 TVs, how many of them are actually good and they work? So to get this, you would do 100 minus 6, which is 94. So now your sample N is going to be 100 TVs, and we're going to select 5 of them to test. So we're looking for the probability of the shipment being accepted, and for it to be accepted, all 5 TVs must be good and working. So that means I want 0 defective, and 5 are going to be good. So just as before, and since we're dealing with probability, I'm going to draw a line. In the denominator is going to be my sample space, which is going to be the 100, choose 5. And then in the numerator, I'm going to have my defective TVs and our good TVs with a C above both. So total defective that we have is 6. And for this problem, I want to select 0 of those. Whereas the good, I know I have 94 total that were good, and we're selecting 5. And means multiplication, so we need to substitute this in on our calculator. On the graphing calculator, I'm going to type in the first digit, which is 94, and go to Math, PRB, our combinations, the NCR. Second digit that we have is a 5. And then again, to get out of that sub part, I'm going to use my right arrow so that it's now a normal spot for the multiplication. So then times. And then the next number that we have is a 6. I'm going to select Math, Probability, NCR, and then I have a 0. Select Enter, and this gives me the result for my numerator. But I'm going to divide this by 100. Combination, so go to Math, PRB, NCR, and then 7, and select Enter. From the graphing calculator and rounding 4 decimal places, we get 0.0034. The example right below says Todd is putting together an exercise routine and feels that the sequence of exercises can affect his overall performance. He has 12 exercises to select from, but only has enough time to do 9. How many different exercise routines could he put together? Now, most of us might think that the order doesn't matter here, but he believes that the sequence of the exercises is going to affect his performance. So for this one, for Todd, order matters. So this means we are using permutations. And so the total number of exercises that he can select from is 12. And he can only have time to do 9 of them. So we're only selecting 9. On the graphing calculator, we're going to type in 12, go to Math, go to PRB, select Permutations, and make sure to select 9 for our second digit and Enter. We get an answer of 79,833,600, and these are exercise routines. The last question here says, suppose the passcode for your iPhone is a 4-digit long sequence. It says, what is the probability that a classmate correctly guesses your iPhone passcode? So the first thing we need to figure out is that denominator number. And so for that, there is 4 digits that we have. These are all numbers. And with your passcode, the numbers could repeat. So you could have 0000. And so that means there's 10 digits that can go in each of these. We are multiplying these. When you do this, you get 10,000. And this is equal to our n. So the probability of correctly guessing the code, so we'll say correct guess, is going to be that 10,000 goes in the denominator, and you have one code that is correct, and so that'd be 1 out of that value that we have for our sample. Dividing this, we get 0.0001. So this is the end of our chapter 4 notes. Make sure that you have watched both videos. All your notes are complete as done in our class videos, and make sure to upload them as a single PDF.